have visits this week of Gabriela Sato-Polito. It's a pleasure to have them here. They're going to give one seminar and colloquium each. And we're going to start today with Gabriela Sato-Polito. Gabriela is her undergraduate at the University of São Paulo. She's a molecular scientist, I guess. She worked with Abramo on her project, an undergraduate project, and she did her PhD at the University of Johns Hopkins with Martin Minkowski. And she's going to talk about, she's now a postdoc at the Institute of Dense Studies in Princeton, and she's going to give a talk on gravitational-wave signatures of supermassive black holes. Thank you, Gabriela, for coming.
Thank you. Yes, I'll be talking about pulsar timing arrays and low-frequency gravitational wave measurements using this technique. And I'm going to start by talking about how the detector works, basically. So I'm going to start with the detector, how observations of pulsars can be used to measure gravitational waves. Then I'll talk a little bit about the sources, and in particular, basically the only astrophysical source are supermassive black holes that are merging and slowly spiraling. So I'll talk a little bit about how we think about these systems, what we know about them, and then I'll discuss how we can basically predict what we think that pulsar timing arrays should be observing. Predicting PTA observables. Okay, I'll talk about two kind of recent papers on this topic. I'll just write down the phone numbers for them over here. In case people want to take a look. And these are works that were done in collaboration with Matthias Albriaga and Elliot Waters. So these are kind of the main works I'll be discussing today. Okay. So pulsar timing arrays rely on observations of pulsars, which are these spinning neutron stars. So they're neutron stars that emit jets of radiation, and they rotate with very stable periods. Every time this jet faces your line of sight, you see a little pulse. So let's say we're here on Earth, we observe some pulsar. These are typically in our galaxy, and they have their jets. This is basically like a lighthouse. I would call this lighthouse model of pulsars. And every time this beam faces the line of sight, you see a little pulse. These are typically observed in radio frequencies, where pulsars are brightest, and they propagate to us on Earth, over here. And these periods, these are millisecond pulsars, so these pulsars have a period, ICTP, of roughly a millisecond. And we observe them in the galaxy. These are galactic pulsars. And the idea is that if you have a gravitational wave propagating from some distant source, let's call this direction to the pulsar p hat, and the direction of the gravitational wave emission is called omega hat. The passage of this gravitational wave through this Earth pulsar baseline will perturb the path of your pulses on their way to us. I'll just mention a few scales just to have kind of a sense of the physical dimensions of this gravitational wave detector. So the pulsars are typically, let's call this distance LP. And LP is an order of a kiloparsec. And these distances are much larger than the wavelength of the gravitational waves that are passing through through. So this is much larger than when the gravitational waves that this system is sensitive to. So these are typically on nanohertz frequencies, so the wavelength is around 1 to 10 parsecs. This is a different regime than, for example, LIGO is, where the length of the interferometer is much shorter than the wavelength of the gravitational wave. And again, these are nanohertz gravitational waves, so the period is roughly, let's say t gravitational wave is roughly 1 to 10 years, let's say. And this is much larger than the period of the pulsar, which again was around a millisecond. So these are very long wavelength modulations, and you're basically observing these pulses that are kind of ticks in a clock, right? You think of these pulsars as just clocks in the galaxy. Okay, this is just some physical scales. The sources are typically coming from much farther away, right? These are, as we'll see, these are supermassive black holes that are maximum cosmological distances. So they'll be, say, the distance to the source, let's say, is going to be something like, I don't know, gigaparsec versus the distance to the pulsar, which is much smaller. Okay, so let's say you have, so this period is the intrinsic period of the pulsar, and you can build models for what the arrival time of these pulses should be. And let's say you think that it would have arrived here on Earth at some time t and some other time t prime for these two pulses. And when you observe them in the presence of gravitational wave, this arrival time will be perturbed. So you're going to see some t plus some delta t, and this residual, this change in the arrival time that you observe is something of the order of the gravitational wave amplitude integrated along this path that it propagated through. Okay, so this is something of order t, delta t, and here it arrives at some delta t prime. And so the intrinsic periods would be something like t prime minus t, and the observed period, including this shift from the presence of the gravitational wave, will induce a shift in the observed period of the pulsar that is some delta t. Okay, so the interesting quantity to think about is then some redshift, some observed redshift in the period of the pulsar, which is this change in the observed period, this relative change in the observed period, okay, that is induced by the presence of gravitational waves. And if you follow through this calculation, you can show that this is given by a projection of the gravitational wave along this Earth pulsar axis. So you get some geometrical term here that goes as p hat I, p hat j, and then omega hat, again, is the direction of propagation of the gravitational wave times p hat, and then the difference between the metric perturbation on Earth and at the pulsar. So HIJ, and then at some time at the location of the Earth, which we can just define to be the origin, and then minus the metric perturbation at the pulsar, so some retarded time, d times L p, and then the location of the pulsar, which is L p hat. Okay? So this is the redshift induced by gravitational waves on your pulsars. And I'm going to take here the chance to just define your quantity. So I'm just going to write this as the antenna beam patterns, which I'll write down explicitly in a second. So this is F plus, the change in the metric perturbation, of plus polarization of gravitational waves, this is across. So this again is just the difference between the metric perturbation on Earth and at the pulsar. And this F quantity that I've defined here is just are the attendant beam patterns, which are usually defined in the literature. And this is just given by the combination of these geometric factors that you can see over here, having written the metric perturbation in terms of the gravitational wave polarizations. So plus cross is equal to p hat I hat j. Polarization tensor plus or cross, I think. So this is just grouping all of these geometric factors that we had before, and I've written here hij. The metric perturbation in terms of the polarization tensors, grouped all of these geometric factors into F, plus and cross, and then these are just the difference between the metric perturbation on Earth and at the pulsar. Okay?
So the hat just means the vector, is that what the hat means? On P?
Yes. Yeah, it's the unit vector in the direction of the pulsar. So this is just projecting the gravitational wave along this axis.
So why do you say unit vector?
Sorry?
It's just the vector, it's not a unit vector. P hat is squared is 1? Is that what you mean?
Yeah. Yeah. So this is just, this is the unit vector. So the position of the pulsar is just LP times P hat. Okay.
So this is just the geodesic equation, comes from the geodesic equation of the photon that the pulsar is shooting at us.
Okay, I'm gonna erase. Yeah, maybe I'll erase that. So in this picture, we were thinking about the propagation of one gravitational wave coming from some direction, omega hat. But we want to describe the scenario where you have gravitational waves coming from every direction in the sky, and you can just write this as a superposition of plane waves. So this generalizes pretty easily. So I'm also going to take the Fourier transform of this z of t. So I'm going to write z tilde of f. I'm going to write this as a superposition of plane waves coming from every direction omega hat in the sky. So integral to omega hat, and I'm going to already use this notation. So I'm going to write this as a sum of our polarization tensors, or of our polarizations, plus and cross. So capital A here is plus and cross of the metric perturbation, again with the Fourier transform, A of F, and this is coming from some direction omega hat that I'm integrating over, F A. And this also depends on the direction of the pulsar. I've omitted this label here, but generically this will depend on the direction p hat as we have over there. So maybe, for the future, I'll just say this is for some pulsar A. A labels the number of pulsars that you have in your array, and this will depend on what pulsar you're talking about. And now, this difference between the metric perturbation on Earth and at the pulsar is just a phase difference. So I can mark this as 1 minus e and it's the phase corresponding to, the phase of the wave here versus when it arrives at the pulsar. So this ends up being 2 pi gravitational wave frequency, then the distance that it propagates, which is LP 1 plus beta hat. Okay, so this is just the phase difference in the wave from one place to the other.
Is P hat constant in time? Does the pulsar always stay in the same position?
So you, not quite, but you move to a reference frame where they are. So you do have to think about the distance between you and the pulsar and the Earth. You have here your radio telescope that you're using to measure the pulsar, and the Earth is going around the sun, everything is moving. There is motion between the Earth and the pulsar, but you have to model that.
So P hat omega hat is constant? P hat
We're assuming it's constant, yeah.
But is it constant?
Well, again, there's motion between the solar system and the pulsar.
But not between the solar system and the gravitational wave.
Yeah, the gravitational wave is assumed to be coming from very far away.
So but on the scale of the gravitational wave is years. So on that scale, P hat omega hat doesn't change?
Yeah.
It doesn't. Okay.
No, it doesn't. Okay. Right, so this is the expression for the Fourier transform of the timing residual of the redshift. And if you're thinking about a single gravitational wave, you might want to describe this in terms of some mass, distance, some individual set of parameters that characterizes the gravitational wave amplitude that you expect to see. But in the regime where you have many sources, say either from many supermassive black holes from every direction or some cosmological background, that's no longer practical. And you really want to think about these plus and cross gravitational wave amplitudes as statistical fields. So instead of asking, what mass or distance of binary produced the source, I want to ask, what are the statistical properties of this field that is defined in every direction of the sky?
You just said that. Thanks.
Okay, so this is a sum of plane waves, so the mean of this field is 0. But it has non-zero variance. The variance is the largest, is the lowest non-zero moment. And I'm going to make a few assumptions about what the general properties of these, of this variance are. So I can write the variance of H tilde for some polarization A, has some frequency, and omega hat. The variance of this thing with some H, A prime, F prime, omega prime. We'll see why this is reasonable in a second, but to a very good approximation, the sources are monochromatic, which means that the frequency emitted in one band has nothing to do with the frequency emitted at another. So I can write this as a delta function in F minus F prime. I can, to first approximation, assume that the sources are unclustered, so the gravitational wave emission from one direction has nothing to do with the gravitational wave emission from a different direction, so I can write another delta function here. I'll assume that the sources are unpolarized, so in the case of supermassive black holes, there's no preference for, say, what direction your binary is facing. So the statistical properties of each of these polarizations, plus and cross, each of them are identical, and they're uncorrelated between each other. So I write this as a delta A prime, and then a power spectral density. So this is the power spectrum, or the covariance between metric perturbations. Okay, so if I assume this, and now I compute the variance, or the covariance, between timing residuals from different pulsars. So if I compute this average of z tilde of some pulsar A and some pulsar B, I'm already going to put F here because only when they're the same is it non-zero. So I can take this expression and plug this in twice of this, and a lot of things cancel out because of these delta functions, and you can show that the final expression that you are left with after doing this will just depend on some amplitude of your power spectral density, F, times an integral over all directions, omega hat, of your antenna beam patterns. So I get an F, let's just write this. Okay, so what I'm saying here is that the covariance between the timing residual, the difference between your expected, or the redshift of your pulses, is just proportional to some overall power spectrum amplitude. It's just a function of frequency. And this is basically related to, say, the energy density in gravitational waves per frequency, or the characteristics term squared. So this is just the total amount of energy in gravitational waves. Times an angular dependence that is only a function. So here I'm integrating over all directions omega hat. So this is just a function between your angles p hat A and p hat B. So it's just a function of the angle between your two pulsars. So this is an angular correlation. See, you can call this theta AB. It's just the angle between two pulsars here, p hat A and p hat B. And this angular dependence, you'll see, is just a function of these geometric quantities that I had to define before. And so it really only depends on the fact that you only have 2 degrees of freedom in GR and the directions between your two pulsars, basically. So you can predict, I'm just going to plot this quantity. And this thing is mostly quadrupolar, this angular correlation between your two pulsars. So C theta AB, theta AB. This is just some function that looks like this. It's mostly quadrupolar. And so what this is saying is basically that if you see pulsars, say they're close together in the sky, coming roughly from the same direction, and one of them is coming, earlier, your pulses are arriving, let's say, later than you expected, then a nearby pulsar will also be having, is also expected to have pulses arriving later than expected. As you change this angle with respect to each other, this correlation goes down. At some point they become anti-correlated, so if one is arriving early, the other is arriving late, and then it goes back up again. So, yeah.
Why you say quadrupolar? I mean, this is dependent on the multipolar approximation. You just use the statistical properties of H. So you're saying nothing about the source, but the direction. So
I'm not saying anything about the source, but I am saying something about these. So it's really just a function of this, and these two things ends up being approximately quadrupolar. It's not exactly quadrupolar.
No, yeah.
So if I were to write this in a harmonic decomposition, this goes as 1 over these two. It goes like this. So it's dominantly quadrupolar, like the largest starts at L equal 2. So it's predominantly quadrupolar, but it's not exactly, like if it were perfectly quadrupolar, it would be something obviously like this. And then, so you have some other higher contributions.
So you're just talking about the legendre and polynomial expansion of that function?
Yeah.
Okay.
So the fact that it goes up again, the correlation has to do with the wavelength of the gravitational wave, or has nothing to do with it? Because you would expect. Sorry, go ahead.
Yeah, so if you were in the LIGO regime, where the wavelength of the gravitational wave is much longer than the arm of the detector, you can actually show this by Taylor expanding this. You end up with a perfect quadrupole here. So this would be a perfect quadrupole. But because you're in this long arm length regime, you get this particular form over here. So it's dependent in that sense. So yeah, if you extend this for a short, wavelength relative to the length of the arm of the detector, this comes down, you cross out the 1, and then you have this 1 plus omega hat times p hat, which cancels with the denominator with this denominator over here. And then p hat I, p hat j, this is perfectly quadrupolar. And so you recover a perfect quadrupole.
I was just trying to get some intuition, because if the angle between the pulsars is very small, then of course they will feel the same way in gravitational wave.
Yeah.
Now if they're far away,
Yeah.
I would expect them to feel indifferently because of the wavelength of the gravitational wave.
So when they are say 180 separated, the thing is that you're integrating over all gravitational wave directions, right? So it's not just one gravitational wave coming, say, from here, but your pulsars are here. It's integrated over the entire sky. And then, basically, so for example, in that regime, so say when I compute ZA, ZB, I get in the denominator 1 plus omega hat P hat A, P hat B. And when they're 180 apart, you get like a 1 plus cosine, 1 minus cosine. When they're together, you get a 1 plus cosine, 1 plus cosine, for example. So they end up being different here, and not go up all the way back to the quadrupole because these two things are different,
Thank you.
Okay, so just to summarize, the covariance between your timing residuals has an amplitude that depends on the total energy density in gravitational waves per log frequency, and an angular correlation that just depends on these geometric considerations. And basically, this shape is then considered strong evidence for gravitational waves if you detect it in your timing residuals, because no other source of noise will produce a pattern that looks like this. So for example, I mentioned that there are multiple sources of noise. One of them is the relative motion between the Earth and Pulsar. There are many others, but none of them produces this roughly quadrupolar shape in the angular correlation. And in 2023, evidence for such an angular correlation was found for the first time in pulsar timing arrays. So multiple PTA collaborations, so Nanograph is the North American one, the European PTA, they combined their data set with the Indian PTA. The Australian one is called Parks PTA, and the Chinese PTA found evidence for such quadrupolar pattern. This was the first time that it was achieved. And was considered some initial evidence for gravitational waves in this frequency regime. Okay.
So these were all the same observation, or they were different waves?
So these are different collaborations. They're based on in different observations from different radio telescopes, but so all options of, so they have common pulsars, they have pulsars that are unique to each of them, and they are independent analyses of each other. Okay, so now I'm going to talk a little bit about what this means what we know about the sources or what we expect to see.
I mean, aside from saying that they all saw things, is there any other way of saying, you know, how frequently they saw them just to compare the different experiments?
What do you mean, how frequently?
I don't know, so they all saw things.
Yeah.
They all got a positive response, but I would like to have a little more data to say that actually they all saw the same thing. Is there any way to
So the comparisons between them are somewhat preliminary. There was a paper that came out shortly after this initial announcement between the European, the Australian, and Nanograph, sort of comparing their results. And they found, so they compared it only in terms of this overall spectrum that they measured. And the amplitude is roughly consistent between them. And there is so the next step along this route is a joint analysis between all of these where they reanalyze their own data sets with the same set of assumptions. But the amplitude that they find is consistent. Yeah.
So what is the significance of statistical significance?
So the strongest one is Nanograph, which is around 4 sigma. So they're not calling it a detection yet because it's not 5. The other ones are a bit lower, like 2 to 3. Okay. So sources. So from this discussion, the range of gravitational wave frequencies that one can access are related to the total observing time of their pulsars. So the lowest frequency, min, is just equal to 1 over the total observing time, which is roughly a decade. And so this is around an nanometers. And the highest frequency is related to the cadence at which you go back and measure these pulsars. 1 over the cadence. And this is on the scale of weeks to a month. So this is 100 days. And the typical sources that emit gravitational waves in this regime are supermassive black holes. So at the center of every galaxy, there's a supermassive black hole, it turns out. And galaxies merge, so people expect that supermassive black holes at the centers of galaxies would also follow the merger of these host galaxies. And the frequency, so just to get a sense of the scales again that are emitting in this frequency band, just using Kepler's law, and with the fact that the gravitational wave frequency is twice the orbital frequency, you can see that, so that gravitational wave is Kepler's law, total mass, and radius huge. And if you just plug in some relevant numbers, you can see that a 10 to the 9 solar mass black hole at some subparsec orbital separation, so small fraction of a parsec, produces gravitational waves at roughly 10 nanometers. So this is kind of the relevant regime. This is many gravitational radii, so it's very far away from actually merging. And the masses are these billion solar masses of supermassive black holes. So this is kind of the relevant, the typical system that we'll be interested in. And again, you're seeing this very early in spiral. So if you think of the waveform of gravitational waves, you have some very long, slowly evolving in spiral before it actually merges. And in LIGO, you see this part, and in PTAs, you see something over here, but maybe this part. So this is why your sources are broadly to a very good approximation monochromatic, because you're just in this very early spiral, you're very slowly moving and emitting gravitational waves at just a single frequency, basically, throughout your entire observation time, the 50 days.
So there are no other sources, for instance, cosmological phase transitions?
So these are the only astrophysical sources. So anything else would be beyond standard model prediction. That aren't these. Okay.
But you can also have like neutron stars that are rotating and produce these low frequency beams also if they have some.
So the thing is, because the gravitational wave emission scales with mass to the 5/3, this very quickly takes over any other source.
Also, if you want a stellar system, you should be hundreds of parsecs away. The binary system should have a size of hundreds of parsecs. If you think of these figures.
Okay, so for the next, oh yeah.
when you consider that your signal comes from a finite number of astrophysical sources, there's also that popcorn noise, right? Because like it's a finite rate in which they emit, in which they are produced. So does that like change the statistics?
So there's a finite, can you say that again? There's a finite what?
No, yeah, I mean, if you have like a finite number of sources that are superimposed to like, build your signal,
Yeah.
Doesn't that like add some like noise term to the correlation?
Okay, this is actually the thing that I'll talk about. So in the last part of the talk, I'll talk about predicting PTA observables. So PTA. And so I'll start by talking about this overall amplitude, the power spectral density that I had mentioned before. But the second thing I'll talk about is spectral fluctuations. So I'll just write stuff where basically you're observing the spectrum of gravitational waves in some finite frequency ranges, and you have a discrete number of sources producing gravitational waves at each given frequency, right? So from the fact that you have Poisson fluctuations in the number of sources, you predict some fluctuations in the spectrum. So that's the effect of having a finite number of sources that can vary by number. So yeah, this is the topic number 2. But yeah, let me know if you still have questions after that. Okay, so yeah, as I mentioned before, this covariance depends on the overall amplitude of gravitational waves, which is proportional to the average energy density the average energy density of gravitational waves. So I'll start by talking about how we can predict this, and this explains like 90% of what we see in terms of these PTA observations. You're basically just measuring some amplitude of a power law right now with current observations. So I'm just going to call this 3.1 as the amplitude. And so basically the way that you think about it is that the energy density per log frequency in gravitational waves is just equal to the energy produced by a single source summed over the total number of sources. So say there's some set of parameters that I'm going to call theta. So theta in practice is going to be something like redshift, say one do it in terms of the total mass and the mass ratio of your systems, for example. Some set of relevant parameters that describe your signal. This is the total energy density is just going to be equal to the number density of these sources per relevant parameters times the energy produced by each source for log frequency. And if this is in the rest frame, we get an additional 1% here that the energy loses. And then the rest frame frequency is 1 plus the observed frequency. Okay? And this energy, the only frequency dependence of this quantity comes in this energy produced per log frequency. And we expect that in this in-spiral regime, the motion, the dynamics of your binary is just determined by gravitational radiation. So we know how to predict this energy loss exactly. And so you just equate the power radiated with gravitational waves with the energy, the change in the orbital energy, you use Kepler's law, and then you find that dE T log F equal to something like shear mass divided by 5/3, frequency divided by 2/3. And chirp mass, I guess just some definitions. Eta is the symmetric mass ratio. Just some definitions between total mass, chirp mass. This is the symmetric mass ratio, which is defined like this. Q is the ratio between the two constituent masses. Okay. All right, so we know how to predict this energy per log frequency, this energy spectrum produced by each source exactly. And if you then put this back in here, I'll also use I'll switch over to the characteristic strain instead of the energy density. So the strain is basically, this is just the energy in, like the energy density versus, say, the amplitude of the gravitational waves. Okay, so this is the frequency dependence. Again, your R is equals 1 plus C F. So this is, you get a factor of 1 plus Z to the 2/3, F to the 2/3. And if I plug this expression back in here, and I move to the characteristic strain as a function of frequency, you can show that this is just F to the minus 4/3 times the integral over my number density. I get a d theta, dn theta, a factor of 1 plus z to the 1 minus 1/3 from this 1 plus z here, and that one over there, and mass, chirp mass to the 5/3. Okay, so this shows that from our understanding of how the systems evolve, we can predict what the frequency dependence of this signal should be exactly. And basically the only thing we don't know is this quantity over here, right? This is what you need to be concerned with if you want to predict what the average spectrum you should see in pulsar timing arrays. So basically, your prediction for the characteristic strain as a function of frequency is just this power law, and you don't know what this amplitude is, but you know that it has to go more or less as that 2 minus 1. And so the question now is how do we model this quantity over here, the co-moving number density, which is the main thing that we don't know. And let's do that. it turns out that there's a very simple way to predict what this quantity should be. If we know what the number density of black holes is today, which is something we can directly observe. So the kind of key insight is that if you imagine, so there are many approaches that one could take to do this. You could, for example, imagine describing like the merger of dark matter halos and paste on a black hole and try to model this whole evolution. But this introduces a lot of uncertainties because you need to specify some connection between your black holes and your galaxies and your halos as a function of redshift. You need to know how long they take to merge and so forth. So you sort of accumulate a lot of uncertainties. But you don't have to do that because we can measure the number, the mass function of black holes, just single black holes, of supermassive black holes today, like at redshift 0, in our local universe. And whatever merger history that these black holes had, they need to result in the mass function that we see today. Okay, so just, I don't know, if you have some light cone and you see the single final population of black holes here today, you just assume that in the past they had to merge to produce the gravitational wave signal that you saw before, and this leads to the population that we see around us. Okay? So if you imagine that these black holes that exist at redshift 0 just merged once in the history of the universe, then this mass function that we can measure directly is just equal to the number of binaries. I'm going to call this single non-binary as a function of total mass at some other redshift, right? So you still have to specify what redshift that these black holes merged in, but if they just would merge once, then you know that the mass dependence is just exactly equal to this directly observable quantity over here. So this allows you to rewrite this expression, not in terms of this co-moving merger rate density of black holes that you might not know how to model exactly, but just as a function of the number of black holes that you can measure today. So I would write this quantity, I'm going to rewrite hc squared as equal to f to the minus 4/3. And then I still have to specify some redshift distribution over here. So this is, again, a dz, dmass, dq. So I'm going to write this as an average over the redshift distribution of 1 plus z to the minus 1/3. MC, the Church mass, just gets a factor of, I'm just going to convert this into mass ratio and total mass. So this is an average over eta, the symmetric mass ratio, over the mass ratio distribution, times this integral of dm total mass to the 5/3, dn total mass. Where now this, I can just measure directly, and these are averages over some assumed distribution, but this means that it's very easy to take an upper limit, right? If you wanted to know what is the maximum amplitude that you can predict, you can just take this redshift to be 0, this mass ratio to be 1/4 is the largest possible number, and so what this means is that there's always a maximum gravitational wave amplitude that you could possibly predict for the gravitational wave background if you know what the mass function today is, which we do. Okay, so there's a very simple interpretation of what this amplitude should be, and there's just a strict upper limit in the amplitude of gravitational waves.
So these averages are over some probability distribution that is redshift dependent?
It is not redshift. So this is for example, this is the redshift distribution of this one merger, right? I'm saying there was one merger in the universe, and this is the redshift distribution at which they occurred.
Right, but the theta there can also be redshift, right? So there's
Theta.
one of the parameters is redshift.
Yes.
So
Which is where this average came from, right? I just wrote integral dz, dm, dq, dn. So there's rho theta, yeah.
Right, there is a redshift there, yes. Yes.
Yeah.
Yes, so that's what I mean by being redshift dependent, the NTZ there. So, yeah, so the average is redshift dependent because it depends on the NTZ.
You're saying, for example, if the distribution of masses depends on the redshift. Yeah. So here I've assumed by construction that there's only one merger. And so, but you could imagine that there is some dependence. For example, say lower mass black holes merge earlier in the universe. You could not, I assumed a separation here between the redshift distribution and the mass distribution, for example. But again, if you wanted to just take an upper limit, this is the most you could possibly do, right? The largest amplitude is just if every single one of your black holes merged now, right?
Sorry, I'm just, maybe, I don't know anything about black holes, but why do you assume that each one merges? Do you have to merge to be a black hole, or what's?
You don't have to merge, but you do have to merge to produce the gravitational wave.
Right, so why are you allowed to assume that each black hole that exists today merged once? What's the rationale behind that assumption?
So what we're going to see is that even if they merge an infinite number of times, you don't produce an infinite amount of gravitational waves, it saturates at some point. So the point here is just to show that there is an upper limit. Whatever you want to do, there's always an upper limit. They don't have to merge even at all. They could merge 0 times, in which case you produce no gravitational waves. So there's no, it's not mandatory, but it's just how you predict an upper limit.
Sorry.
Yeah.
Where exactly comes the z scaling? Where does it come from exactly? The 1 plus z to the minus 1/3?
Yeah, that's just there's a 1 plus c here.
Right.
And then in the energy spectrum, because this depends on the rest frame frequency, you get a 1 plus c to the 2/3, so then over there you get 1 plus
Okay, so you're not assuming that the distribution goes, sorry, it's an average, you just have to put the p there.
Exactly. Yeah, this average is just, yeah, it's an integral of dc and the probability distribution of z, 1 plus c, minus 1/3.
And what do you take for PLZ?
So for the upper limit, you can just take a delta function in z equals 0, and that's the maximum possible amplitude. For the fiducial prediction, we adopt some distribution from a simulation, but they're generally very peaked at low redshifts, just because of hierarchical structure formation.
And anyway, it would be just a number for the unit.
Yeah. And this is very insensitive, right? 1 plus c to the minus 1/3 is a very low power. So you can change the merger history by a lot, and you don't change your prediction by very much.
Suppose you had many mergers.
Yeah.
Why wouldn't that raise the maximum limit?
Yeah, so good. So this assumes one merger. If you have multiple mergers, you can think of this as, you ended up with the final black hole mass here. And you're saying, let's just say that they merged with equal mass companions, because that maximizes your signal. So here you have 2 and 2. And now, this is the only thing I considered, but now say I want to split this more into smaller black holes. Again, because the gravitational wave signal scales as mass to the 5/3, you're always making smaller black holes, so they contribute less and less to the total. And you can write this as a series, and it turns out that even for an infinite number of mergers, you can show that the strain, let's just say strain, for an infinite number of mergers, so I wrote this as a series, took the limit to infinity, it's 60% larger than this one prediction of one merger, okay? So it really doesn't change the picture very much. And the other comment is that this integral is, again, you're integrating over a mass function and some mass to the 5/3. This kernel, if I were to plot it, is very strongly peaked at some characteristic mass. So this is the kernel, let's say hc² kernel. And this is, let's say, log mass. And this is 9.5. This is strongly peaked at some characteristic mass. So if I want to make any statement based on, say, observations of this mass, function, I don't even need to care about the whole range of black holes that could exist. I only need to care about some very narrow range of masses that are pretty well observed. These are like the most massive galaxies in the universe. We see them pretty well.
And what is this density nowadays? 10 to the minus 3 per megaparsec cube?
Yeah, 10 to the, I think 10 to the minus 4. It's like past this exponential fall off of some Schnecker function. It's around 10 to the minus 4, I think.
Per megaparsec?
Yeah, per megaparsec. Yeah.
And they speak around 10 to the 10-ish.
Yeah, a few times 10 to the 9. Yeah, so, okay, in this paper, this is what we do. We take these observations of mass functions, and we predict the maximum gravitational wave amplitude that one would expect. And it turns out that right now, this maximum amplitude is a bit lower than the observations, which we found kind of curious. And I'll show this in more detail in the colloquium as well. So I'll show a actual plot, not a hand-drawn version of this. But yeah, basically, if I take some observations of the mass function, and I look at this characteristic strain, these predictions say would end up here, and the PTA observations are here. Okay, this is some 10 to the minus 15, like a few times 10 to the minus 15.
Sorry, Gabriela, tell us again where the observations of the mass function comes from.
Like how they're obtained. So the observations of the mass function basically, so if we could, in our local universe, we can look at very nearby galaxies, and when we have sufficient angular resolution, you can directly measure the kinematics of stars around a central potential, right? So you can see, stars are gas, and you can infer the mass of the central potential kinematically.
For very local galaxies.
Yeah, so this is true for galaxies like below 100 megaparsec in distance. So there's like 100 and something galaxies where these types of measurements that are considered the most reliable are possible. And so what you do, you can't measure a mass function from 100 galaxies, unfortunately. So what you have to do is that you measure some scaling relation between some property of the galaxy that you can more easily measure. So for example, the velocity dispersion of the host galaxy, or the stellar mass of the galaxy, or some luminosity. And for this sample of galaxies, you can have you can build a relation between these properties and your black hole mass, some power law, some scatter, and then you just look at a larger galaxy sample and you count galaxies as a function of this. And so your dn to the black hole mass is just equal to some whatever property times x.
So I have a proxy for the
Alright, so this is measured from some larger galaxy sample. This is some PDF or some scaling relation calibrated in some local galaxy sample, and then you predict your total by just combining these things.
And the error bars there reflect uncertainties, scatter.
Yeah, and it's totally dominated by the errors in the scaling relation. Like pretty simple, like old galaxy surveys could already measure this very well, because it's not a very demanding statistical measurement. So we've been kind of curious about this. These are kind of new observations, so there's a lot of room for error. But I think, if you want to understand what is producing the gravitational waves in this regime, I think this is a very clear avenue to do that.
But are you really worried by a factor of 2?
So it's a factor of 2 in the strain, so it's that squared in the number of black holes. So this is a factor of like 4 to 10 in number of sources.
Do you think in your formalism it would also be possible to include the eccentricity? It would not help much actually.
Yeah, people do.
Because the spectrum is not very compatible with circular binaries.
Yeah, so the spectrum in, for example, in nanograph, you see, this is what you're talking about. So in the spectrum in nanograph, you do see, I mean, it's very noisy, but let's say something like the power law, and then the first point is a little bit lower, and eccentricities can do that. And there are people, it is included in some models.
But in your one, is it something you could
It's something that we could include. It only affects this very first, at most this very first thing, and it generally attenuates the signal.
Yeah, so it would not help
Yeah.
here for the shape.
Yeah. I mean, it's not a huge, there's certainly room for these things to eventually come in agreement. But right now, your best estimate is somewhat off.
I mean, my question in general is, in your formalism, can you include easily things that can also, because you mentioned a lot about the object itself, but
Yeah.
with the shape, it's very not. So there are just like environmental effects that could, so other things that you could easily plug in to investigate how they change the spectrum.
Yeah, the environmental effects, again, these are all things that change this low frequency regime, but you could basically change, it introduces, I mean, I guess the answer is yes. We did it in these predictions, but it's very generalizable, yeah.
Okay.
Okay, so finally, how much time do I have? Yeah. Yeah. Sorry. Yeah, the slope is much less well measured than the amplitude. So the thing, I think I maybe ran out of time. I'm not sure when we started.
Yeah, plenty of time.
Okay. Yeah, so the slope is not as well measured, but there's more information you can get out of looking at the full spectrum. And that's what I'm going to comment on right now. The slope that they find seems to be a little bit shallower, but it also seems to be very degenerate with noise models in pulsars. So it's a less robust measurement, I think, than the overall amplitude. Most analyses find somewhat consistent results for the amplitude where the signal to noise is actually, where there is signal to noise, basically.
So the slope at low frequency is compatible with the positive slope? No, in the data.
Yeah, it is. It's just a little bit shallower. They're statistically consistent to within. They're like, I don't know, 2-3 sigma of this like -4/3 of the characteristics.
But it's not definitely negative at
No.
the slope.
Yeah, it's just a little bit shallower. Yeah. But yeah, again, it does seem to be, the slope seems to not be particularly well measured and seems to be kind of degenerate with some systematics. But okay, if we do have this information, this full spectral information, so I'm going to move on to this point number 2 over here, and I'll try to go through it somewhat quickly and just schematically mention how we deal with this. So you do see the full spectrum, right? You have some range, and the range where there is any detection is somewhat limited, but you do see some, not just one point, but you have some measurements here by days, and let's say this is your predicted power law, like this. But you do have this spectral information, and one additional step you could do is to think of the fact that the actual realization that your measurement is one realization of the sky, right? So this prediction in terms of the power law, the average power law amplitude, and the mean number of sources will give you some average number density of sources and the average gravitational wave spectrum that you expect to see. But your actual sky is just one realization of this, and you can have Poisson fluctuations in the number of sources that contribute to each frequency bin. So the idea is that instead of thinking of this characteristic string as this integral over the number of sources of the mean co-moving number density of sources times this mean energy density per source, and this is some average value in the universe. I can rewrite this as some total number, and this is just some volume factor times some amount of time that you spend per frequency bin, d theta, of the total number of sources in the universe, d theta per frequency bin, f, times some flux per source that you predict, which is itself a function of mass, redshift, so forth. And you're really describing this as, let's say, some finite frequency band here, and you're imagining that there's some finite number of sources, each of them contributes some amplitude here that add up to this total value that you see, okay? So this HS is basically a flux that each source produces, and your observation is a sum of this flux. I'm just going to write HS is, well, it's just proportional mass to the 10 thirds. Some luminosity distance, and this is per log frequency, d log frequency. If you have some finite bin, you're looking at the number of sources integrated over some finite, say, band pass, and your sources that were some delta function in frequency also get spread out over this finite band pass. So you also get divided by the frequency band that you're observing in. Okay? This is just if you have some finite that you observe here in.
It's minus 1/4. Minus.
No, it's 4/3.
Plus?
Yeah. Yeah. It's just that your frequency, so this is just the power, this is like the amplitude, right? This is like some your h plus h cross is proportional to the mass of the 5/3 frequency to the 2/3, right? Okay. Yeah, here there's also a frequency dependence in the number of sources because they spend a certain amount of time in each frequency bin. So this also has a frequency dependence in it. That backs out to the minus 4/3 over here. Okay, so the idea of so what you want to do is, given some model of the number of sources, to be able to predict this probability distribution of the total characteristic strain per frequency bin, right? Before we were just considering the mean of this distribution, let's say ht squared is equal to this. But what we want to do is to consider this full distribution and then compare that with the data. And the reason why you then get a distribution is because this number of sources can have Poisson fluctuations in your actual realization of the universe. And I'm gonna try to wrap this quickly.
So the mean doesn't change, only
Yeah.
error bars will change.
Exactly. The mean that you predict is the same, but you have some distribution at each frequency that you compare. And there are basically two effects that these Poisson fluctuations induce, which then allow you to say something more about your sources than just the overall amplitude. And these two effects are basically that you expect to see some frequency-to-frequency fluctuation just from the fact that there is some Poisson fluctuation in the number of sources. So one is this frequency-to-frequency fluctuation, and number two is that actually the number of sources falls as a function of frequency. So this quantity here falls very strongly as a function of frequency. So this Poisson fluctuation, the Poisson fluctuations become more prominent as you go to higher frequencies, and the median actually drops off. So as you decrease the number of sources, your distribution becomes more and more skewed. So say you have many sources, you have some roughly Gaussian looking thing. As you decrease the number of sources, this becomes more skewed. And even if the mean is the same, the median over here is lower. So you actually expect this to drop off faster than the power law in a typical realization of the universe. Yeah, if you guys want me to stop now, I could just stop. I think I've gone over it too much. But
Okay, I heard.
No, we're not.
okay. Okay. Right. So the idea is to describe the emission in each frequency then as the sum of the emission from each individual source. So HT per min is just the sum of the emission of each source that is contributing. And what you want to compute is the probability distribution of the sum of random variables, where each random variable is drawn from some probability, from some single source probability distribution. So instead of working with the number, instead of working with this whole number of sources per all of these parameters, so this multidimensional distribution of sources, you can instead change variables to some number of sources per each s squared per log frequency. So you can just, given this relation between all of your different parameters, you can just change variables from this multidimensional thing to just per source brightness.
Just a quick question.
Yeah.
So the central limit theorem would say that HT follows a Gaussian, HT squared follows a Gaussian distribution.
Yeah, if you have many sources, right? But if you have some distribution where a small number of things contribute a lot more than the larger number of things, then you get something that becomes non-Gaussian. Yeah. So it depends a lot on the table, right, of these distributions. So step number one is to not work with all of these many number of variables, but to change this entity. This is basically equivalent to, say, a luminosity function of gravitational waves, right? There's the number of sources per brightness in gravitational waves. And each of these sources is drawn from this luminosity function. So, and I'm just going to omit this frequency dependence here. Every single one of these distributions will depend on frequency, but so I'll just not carry this dy/f with me, but all of this will be a function of that. Okay? So first, we compute this, and you can see what these luminosity functions look like, and their shape is, very similar to the shape of the of these distributions that you had before. And similarly to how the mass kernel has some peak at some characteristic mass, this will have some peak at some characteristic number of sources, right? So if I were to plot h s squared, dn, dhs, this is strongly peaked at some peak, say h squared peak. Okay, so there's also some most important strain amplitude that dominates your prediction for that dominates your prediction actually for the mean number, for the mean characteristic strain. So the integral of this is just the mean strain. And a useful thing to define is this characteristic number of sources, which is just the total, so the mean h bar t squared, which is just the integral of this, divided by the peak. So in other words, if all of my signal were produced by just this most important source, how many would I need? And this parameter controls all of these effects that I was talking about. Right? If NC is very large, then many sources are relevant to your signal, and you're in this Gaussian regime, which is typically observed in low frequencies, versus if NC is very small, then Poisson fluctuations become very important, and all of this stuff starts to happen, your distribution becomes skewed, etc. So this parameter, and whether it's close to 1 or not, is what controls all of this. And this is basically the second thing you can measure, besides the mean that I was talking about so far. So this summarizes all of your observations into a very small number of effective parameters. And this quantity you can show is also strongly dependent on your models and in your frequency. So for example, in terms of this peak mass that I had before, this characteristic number of sources is also proportional to the peak mass, to the -5/3. So the more you're dominated by very massive sources, the lower your NC is going to be, and it's a very strong function of the scaling. And it's also a function of the frequency to the -11 hertz. So this falls off very strongly with frequency, and it covers a very large dynamical range, right? And this is why it's somewhat likely that you cross 1 at some range of your frequency regime, and why this sort of effect can be very important. Where you would see this effect happening within your PTA band, right? If you measure, say, a decade in frequency, your number of sources can change whether forward or back. So
what is the factor that adjusts the dimensions there? Because it tells you what is the frequency of transition, huh?
Yeah, so I can write this for, it depends on what you want to keep fixed. So for example, if suppose I want to keep the strain fixed, say we measure this relatively okay, and this is proportional to some normalization in the mass function, let's just call this n bar, I guess. This is proportional to this peak mass, to the 5/3. Well, yeah. Let's just say this is proportional to this combination of parameters. And say I want to keep this quantity fixed. NC, you can show, is order 1 for the strain normalized to a frequency of 1 inverse year. This is the measured value of the homograph. So this is, if you rescale it in terms of the characteristic strain.
So characteristic strain is dimensionless for you, is it?
Yeah.
And HS2.
Yes.
Okay.
Yeah, all of this is dimensionless. So for if the peak mass is around 10 to the 10, at the very lowest frequencies detected by PTAs, which is like the 3rd inverse year, this becomes order 1. So if it's 10 to the 10,
well in the middle of PTA band, basically.
This is kind of the lowest, one of the lowest frequencies. This is, yeah. So it would be very, which is where most of this, it's 10 So this is like these first few things where you actually detect things really well.
So as I said, the trick is associated with 3 years, and there are a few pulsars that have been observed for much longer than 3 years.
Sorry, say what?
So, I mean, most of the pulsars have been observed for years.
Yes, but the signal is much larger at lower frequencies, so the
Sure.
signal to noise is highest at those frequencies, which is why we just normalize it in terms of these lowest frequencies, yeah. So basically this is where it becomes important. So this is where most of your sensitivity is, and it becomes important roughly at 10 to the 10. So 10 to the 10 peak mass is kind of the scale at which you would sort of start to expect seeing these effects be observable in PTAs. Okay, then, right, so this is your luminosity function, and you can think of this as the PDF of one source. So the probability that one source produces some strain h squared, if the number of sources is equal to 1, is equal to just 1 over n bar dn dHs squared, right? H squared. Now we want to describe this probability of the sum, right? So if I want to predict the probability that some total strain squared given some other number of sources, this is just a convolution, NS convolutions of the PDF of the one source. This is just P is equal to P1 of H squared. This is just NS convolutions of P1 with itself. Okay? NS times. And if I want to describe the probability of this total, then I just need to compute the probability that there are NS sources. So the probability of there being NS sources given some mean value is just a Poisson distribution. So this is P Poisson. Right? Probability of there being NS sources given that the mean is n bar times the probability that these NS sources produce a total ht squared, which is just this quantity over here. And then summed over every possible value of NS. Right? This is the probability of the total. And you can just compute this. It becomes very easy if you take the Fourier transform and compute characteristic functions. So now you can predict all of these distributions exactly, and you just need to plug in your luminosity functions, and now you can predict the PTA observables. One thing that we show is that, so if you do this, and you compare it, you can use these predictions to fit these model parameters, which again, you just need 2 of them. You just need h bar t, the mean squared, and this characteristic number of sources. And this describes all of your predictions. So in this second work, this is what we do. We refit the nanograv spectrum using these models. And you can basically see that there's already a little bit of information. You can constrain NC a little bit, the same way that you can constrain the power law spectrum a little bit. This is it's like an interesting thing you can find. So if I were to plot this into now the peak mass, and say some total number, you can think of this as this normalization of your mass function, or you can think of this as some total mass density in black holes. We show that you can find some constraints in terms of for nanograv in this plane, and that you would predict for your mass functions. So this would be, say, functions, and then this is the prediction for monochrome. In this plane, if you just measure the total characteristic strain, you just find some line here. So this is just the degeneracy of the total amplitude in gravitational waves, and the direction of degeneracy of the characteristic number of sources is something like this. And you can constrain the fact that you have some contour that is squished along this end means that you can already measure some characteristic number of sources. This is and it's basically the same scale here, right? It's roughly, you place an upper limit on the peak mass being something below 10 to the 10, because otherwise you would have seen it. So you don't find any evidence for this type of fluctuation in the spectrum, in nanograph spectrum right now. And so you put an upper limit on this characteristic number of sources. Yeah, that's, so we place these constraints on the overall amplitude of the typical number of sources.
Questions for Gabriela?
Start with Gabi. Gabi, do you have any questions?
Any further questions?
I have one question. Do you mind repeating your explanation on why there is a drop off at higher frequencies in that plot?
Yes. So the effects of Poisson fluctuations are determined by this characteristic number of sources that contribute, and the number of sources falls as a function of frequency. So over here you have a lot more sources that contribute. Say this is the regime where you have many sources that contribute mostly at the same level, versus here you can have a large number of sources that are very faint, but then one rare, very bright source that contributes very highly. So the distribution that you predict, you can show that if you predict this distribution, P of H total, and say you normalize everything to the same mean, okay? In the regime where NC is very large, this becomes roughly Gaussian. Here at some HRT. But as you make NC smaller and smaller, your distribution starts to become skewed. This is a very small, say, order 1. And this is basically because there's some large number of sources that contributes and produces this, say, this lump over here. But you have a very high tail for this distribution, which is basically, this part is basically the individual source probability. So this is, if your P1, the thing you're calling P1 here, goes as some power law, this is the same power law, and it's just the probability that you sample one very bright source, or not. So all of these have the same mean, but the median is changing and is becoming lower and lower as NC becomes lower. And so basically in any realization of the universe, these many faint sources will always be there. Like the probability that you don't see them is basically 0 because there's so many of them. But your mean is dominated by this rare tail, and most of the time you sample 0, right? It's a thing that you sample either 1 or 0, and when you sample 1, you get something over here, but when you sample 0, you get something here, and so your median becomes lower. So most of the time you see something that looks like this, and then sometimes you sample some very bright source, and then you see an excess over there. But the mean, the power law, is dominated by this very, very pale.
Do I know the amplitude that you quoted when you say it was lower than the measured background? Was it at which frequency?
So that was, I mean, you only really see any signal at these, at let's say the first frequency bands.
Yeah.
And so that number is just for the analysis where you fix the power law amplitude.
Right.
And then the amplitude is just dominated by wherever you have signal to noise. So it's for the fixed astrophysical power law amplitude.
Right, but for
Slope.
sure, but at which frequency?
They're normalized, it doesn't matter, right? They're normalized because the power law is fixed. It doesn't really matter what amplitude you're looking at.
Well, because there's a lot of discussion that the second beam to the one of the 1 year could be, for instance, dominated by a single source, right? That it could be a single merger.
But you still,
So that wouldn't be the background.
Yeah, so, I mean, the assumption here is that it is produced by some sum of, you're describing it as a stochastic background, but if you have some rare fluctuation that's captured by this distribution, right? So if you do see some rare fluctuation, then you just weigh models where NC is large or
So I understand
or
that
smaller.
since you're fixing your slope, I mean, divided with the point where you give the values shift, but when you compare to data, right?
Yeah.
That matters because the data over 1 year.
So
I mean, the one over 10 years and one over 1 year are quite different from each other.
yeah, but when you fix the power law, the amplitude that you fit is just dominated by most of your signals and noise, which is just the lowest ones, right? So it's kind of at the inverse 10 years, basically. Like fixing the power law is kind of equivalent to just saying that your amplitude is the value of 1 over 10 years, because that's where all of your sensitivity is. Does that make sense?
Yeah. I mean, I just think that because, well, as we can talk more afterwards.
Yeah. I mean, if you look at this power law, and there's this like 8th frequency band or something, right, that you're referring to that is higher, the power law is here, that band is here. But that band has very little statistical power when you fit your distribution, right? So when you fit your power law.
I think I'm talking more about the free spec. I think about the free spectrum analysis, so where they don't assume any correlation between frequency bit and any form of the distribution. And so you can get something that's clearly not as it is, like not be explained by a single power law. And so that's why I was wondering.
No, but so these models capture precisely that variation, right?
Yeah, but rather this kind of variation at the very low frequencies is exactly right. So if you look at the 1 over 10 years and then 1 over 1 year, it increases at 1 over 1 year compared to 1 over 10 years.
Yeah, but it would be so. Okay, in the first discussion about the amplitude, we just fix the power law slope, and then you're just dominated by the lowest frequency ones. So this point where you have this slightly larger thing becomes irrelevant because all of your fit is just dominated by the first few points. And then in the second analysis with the spectral fluctuation, we take into account the full free spectrum posteriors. And then you're just saying that at each frequency band you have some PDF, right? You have these violin plots. You just have some distribution of the strain.
Yeah.
And you compare each of these distributions with each PDF of the model. So if this fluctuation truly is an individual source, then that's just captured by a PDF with an NC that is small, right? Because those are the only models in which you have any chance of having some large fluctuation. Right? So they're captured by the second.
Okay, so the amplitude to which you compare is the amplitude that they quote when they feed with the power model. That's right.
Yeah.
Okay.
Yeah.
Okay, we can talk more about this later. Okay, so let's thank Gabriela again. And, for those that are interested, go for lunch in 5 minutes. Is that okay, 5 minutes? So meet downstairs at the entrance. Thank you over there. That was a very nice talk. So anyway, we introduce you. Apresentar para o nosso diretor. Por favor,